Paging hardware can also be used to implement virtual memory. Virtual memory is this idea that really, well, one thing we can look at is, let's say that we have a limited amount of physical memory, and yet we want to have a process that has a larger address space, that is, uses more pages than is available in physical memory. How can we do that? And the idea is to go ahead and provide this illusion of virtual memory. Okay. So we're going to use memory as a cache for disk. So memory, expensive, fast, and small. Disks are cheap, slow, and large. So conceptually what we have is our RAM here and our disk, and our RAM is going to be like this window into our larger disk. The basic idea is if we have got some larger amount of virtual space, we can use this RAM to hold the pages that we're actually currently using. So if you figure we've got lots of pages here, but we're only using a small portion of those pages at any given time. And so those portion of pages in any given time can be put in RAM and then can be read and written very quickly. However, if we've got a page that we haven't used have not used recently, so let's look at this as a particular example. So our virtual address space is 2, 3, 4, 5, 6, 7. These should be all even sized. Let's just assume they're even sized pages. So we've got a virtual memory of 7 pages. Okay, and of course our numbers are way shrunk down from what we normally have, where we'd have many, many thousands of pages. And our RAM, let's say, looks like this. So our RAM, or physical memory, can only hold 3 pages. Virtual memory, 7 pages. This is one process. So process A has 7 pages of virtual address space, but there's only 3 pages of physical memory. So what happens? Well, let's say our program is running and has used this page. So let's number these pages from 0 to 6. And let's say it's used, page 0 and page 2 and page 3. So 0 and 2 and 3 would get loaded into physical memory. And that's all working great. So as long as the code of the process is only using pages 0, 2, and 3, and certainly the code is in one of these pages, everything is moving along hunky-dory. The problem occurs where now, let's say the process tries to use some other page. So not 0, not 2, and not 3. Let's say it uses page 4. Well, in order to try and read or write from page 4, we're going to have to replace one of these pages. So we are going to have to take one of these pages and do something with it. All right? Basically, what we can do is put it to disk. So let's say we decide we'll take page 3. So we take 3 and put it on disk. So we take a copy of page 3 and write it to disk, and then fill in page 4. Now, where's page 4 come from? Well, it depends. If page 4, let's say, were a new stack page, then we can just use 0 bytes here, right? Or just random contents of a page. If this page were marked in the ELF file as being initialized with zeros, then we could just initialize it with zeros. So if it was a new heap page, it could be initialized with zeros. If it was a new stack page, it could be initialized with zeros. If it was a global page that's supposed to be initialized with zeros, it'd be initialized with zeros. What about if it's a global page that's supposed to be initialized with other values from the ELF file? Could we get that information about what this should be? We could get that from the ELF file. What if this was code? We can get that from the ELF file. And now we run along. We use this. Why is it that we're not randomly moving all around these pages? It's because of locality. So programs exhibit, normally, locality. Two kinds of locality that they exhibit. Spatial locality. That is, if you are working in a particular address in virtual memory, you're likely to be accessing nearby addresses. That kind of makes sense. If you have an array, how often is it you write a for loop that goes through an array one by one? So therefore, we are exhibiting this locality in the sense that if we just accessed an element in an array in a page, we're likely to access the next element in that page or a previous one. We also see that locality with regards to instructions, where instructions are often either contiguous or near each other, right? Short branches. And we also have temporal locality. So that is shown, for instance, by initialization code. So initialization code is in its own set of pages, and that runs for a while. And then, over time, you don't use that very much anymore, and you start using other pages. So that's a different form of locality. So it's only because of this locality that our virtual memory system is going to work. If our program randomly moved through its address space, then we wouldn't really gain much by having some particular pages in memory. We'd have to keep swapping them out randomly. But we are going to take advantage of the fact that these are the pages that we have used recently, and so they are the pages that we're likely to be needing to use in the future. So think of it kind of as a hit rate for a cache, right? Again, this is a big cache for pages on disk. And so the high hit rate means that our effective access time is about that of physical memory and not that of disk, which is thousands of times slower than physical memory. So we move along, and now we start to we try to access something in page 3 again. What do? Well, we've got to find some candidate to free here in our physical memory. And so let's say we decide to get rid of page 2. So we'll write page 2 to disk. That gives us a free page. And now we can then use page 3. Where do we get contents of page 3? Well, we have it stored right here. This was the last contents of page 3. So if we now move page 3 from disk into memory, then we have the last contents of 3. And so as far as this process is concerned, when it writes or reads from page 3, it has the same page content that it did last time it saw. So as far as the process is concerned, it doesn't really know there's this limited amount of RAM and so on. It's working with virtual addresses, and all it's knowing is that when it tries to read or write in page 3, it's always reading or writing the same contents that have been there in the past. It doesn't know that these contents of page 3 actually took a trip out to disk for a while and then came back from disk. So when we're dealing with a virtual memory, now let's throw in another process. And let's just extend our physical RAM as well. So instead of 3 pages of physical RAM, we'll go ahead and gonna have a lot. We'll have 5. Okay, so process B also has an address space of 7 pages. And let's say this is the contents of physical RAM right now. So we have 3 pages that are in use, and we have 2 free pages. So process B starts executing, and now it needs a page, right? Perhaps it's for the code. So it needs page 0. And I'm just going to distinguish here between A's page 4 and 0 and 3 and B's pages, right? Because we need to make some sort of distinction between them. So we know whose process on this. So page B runs, and we go to the memory. So right, what would happen actually to begin with is we get a page fault here. All of these page table entries would be empty. Okay. So we get a page fault. We need to now go allocate a page. We go to our physical memory, and we try to allocate a page. First thing we look at is there an empty page? Well, thank goodness there is. So we're going to go ahead and allocate a page B0. Where's this going to get initialized from? This happens to be code, and so therefore we're going to read into this from the alpha file. So it's still coming from disk, but it's not coming from a clone of saved pages. It's instead coming from the alpha file. So the alpha file loads B0, process B starts running, and now it needs another page. Let's say maybe it needs some stack. So virtual page 5. So we look, oh, lo and behold, we're lucky. We have a page available. And then it needs a little more, right? It has, let's say, data. So it wants to read from a global variable or write to a global variable. And now we need to go allocate a page. Now's again where the problem occurs of all the pages, all the free pages are gone. We don't have any free pages to use. As we look at these pages, one thing we also can know about these pages is some of them are dirty and some of them are not dirty. Where do we know that information from? We can actually find that from the PTE. I'm going to just kind of mark it next to this here, but notice that this does come from the page table entry. So maybe this one's dirty, and we know B0 is not dirty because that's code and it's not writable, so that can't be dirty. B5 is dirty because we wrote to the stack. And let's say A3, let's say, is not dirty because when we last brought that in, we were doing it for a read rather than a write. So let's say this is the state of things. Process B needs a page. We need to identify a page to replace. What page do we replace? This is, in fact, a big question. So this is, what's your page replacement policy? And there actually is an optimal choice. The one we should get rid of is the one we will need farthest in the future. Okay? So if we had a choice, let's say, between kicking out A0 or A3, well, if we're going to need A0 sooner than A3, we should kick out A3. The problem is we have no idea what's going to happen in the future, right? It's hard to make predictions, especially about the future. Instead, what we can do is say past performance, while no guarantee of future results, is indicative of future results. That is, we can look at which of these pages have we used least recently. Okay? If we've been using something more recently, then we've got this sort of temporal locality that says we should keep it. And so let's say that the order in which we used these was, well, we just used, let's say, B5. This is the most recently used, and this is the least recently used. So that is one page replacement policy, is the LRU policy, right? An MRU policy would be stupid. Say the thing you just used, let's get rid of that, because that is crazy because that's most likely to be used again, we would imagine. So LRU policy says get rid of the one that's been used farthest in the past. And where used, we mean either read or written. That's why it's also nice. It's also nice that the page table entry will actually tell us if a page has been accessed or not. So according to the LRU algorithm, we would get rid of A4. So A4 we have to get rid of. When we look at it, though, it's dirty. So therefore, we need to write it to disk. And these happen to be A's as well. So A4, we write it to disk. When we've written it to disk, right, but at that point, it's no longer dirty. And now we can free it up. And then load in what we were interested in loading, which was B1. So we'll load B1 from data, which means we'll initialize it from B's alpha file. And now B1 is in disk. Of course, we're always updating the page table entry to refer to that as well. And that is the process of page replacement. Notice there's contention here with physical memory between both of these two processes. And it kind of makes sense if one process is actually running, so it's executing, it's got a quantum, a time slice of CPU, that it may be generating more page, it's going to be generating more page usage than one that hasn't run in a while. The amount of multi-programming, that is the number of concurrent processes, is going to control pressure on this physical memory. If you've got just two processes and a lot of memory, then both of these guys, A and B, can both have a large set of pages in memory. And that works great. But as you start increasing the number of processes, you're going to have more and more contention for this memory. In the worst case, you get thrashing. So thrashing is when we have high degree of multiprogramming so that is, we spend more time writing and reading pages from the disk than we do getting useful work done. The way you can tell that is that you suddenly get lots of disk I/O. And you're, again, just not getting much work done. Things sort of slow to a halt. The solution to that, the only real solution, the long-term solution would get more physical memory. A shorter-term solution is reduce how much multiprogramming you have. That is, don't have as many processes running. One way you can do that is you can say, for instance, swap an entire process out to disk or multiple processes. So you say, let's say process A, I'm going to write all your pages out to disk. In this case, just A0 and A3. But I'm not even going to run you for a while, right? I am not going to schedule you to run on the CPU for a while. I'm going to go ahead and let a smaller number of processes go ahead and use the memory without thrashing so that they're getting useful work done. And then once one or more of those processes is finished, I can bring this process back in. So that's the action of last resort when there's just too many processes for a small amount of memory, is just don't even run some of them for a while. Just throw them out to disk, right? Throw their physical pages out to disk and don't even run it, and then bring them back in later. So that is how virtual memory works. Let's look at kind of a flow chart of exactly what's happening. All right, so let's say that a process tries to read or write to some address in its memory. What's going to happen? Well, first what's going to happen is the CPU is going to check the TLB, right, to see whether there's a page table entry in the TLB. If there's a page table in the TLB, then the CPU is going to join the physical address, and away it does its thing, read, write. So that means the page, of course, must be in memory. If the page table entry is not in TLB, then it goes and looks at the page table. And if the page is in main memory, then the TLB gets updated, and again, it generates the physical address. So this is the case where the page is in physical memory. The TLB just didn't happen to have a cache entry referring to it. So this is a slightly slower path than if it were in the TLB, right? Most of the time, the TLB is going to work. We get a high hit rate because, again, of spatial, temporal, and temporal locality. The key is, what if the page is not in main memory, right? By which we mean the P bit is not set, right? The present bit is not set. In that case, we've got to allocate a frame for it, that is a physical page, right? So first question, is there a physical page that's free? If there is a free physical page, then that's fine. The operating system says to the CPU, read the page from disk. It's not always on disk, right? What are our possibilities of where this page comes from, how it gets read? So either this is a page that we've previously had in memory and read and written, in which case its contents have been saved on disk. Or it's from the ELF file. Let's say it's instructions, in which case we can read it from the ELF file that also happens to be on disk. Or if this was a page that we filled with zeros, let's say, and it's still never been written to, then we can just actually right now go ahead and fill it with zeros again. But let's say it's coming from disk, again, either from the ELF file or from our paging file where we're saving all of these pages. In this case, the CPU, right, we activate the I/O hardware and the page gets transferred from disk to main memory. We update the page table and then we return the failed instruction. When we return, we check the TLB. It's not going to be in the TLB. But when we look at the page table, it is in main memory, and then we'll go ahead and be able to read or write to that page. A couple things to note here. So one, when we're activating this I/O hardware, while we are waiting for the page to be transferred from the disk to main memory, do we just sit there waiting? Not at all, right? Imagine, if you will, that we waited, right? A CPU today might run, easily a billion instructions per second. So let's look at the timing. So the CPU went to read or write from memory. So let's say that would take normally about 100 nanoseconds. But instead, we're going to have to wait for reading from disk. And that is going to take, if it's an actual spinning hard disk, it might be as many as 10 milliseconds. 100 nanoseconds, 10 milliseconds. How many instructions could we execute while we're waiting between this time? Right? 10 milliseconds is 10 1,000ths. So this is about 1/100th of a second. Well, in 1 second, we can execute about, I don't know, let's say 1 billion instructions because we run at 1 gigahertz. And so in 100th, we can do about 10 million instructions. So if we wait, we're wasting 10 million instructions. So something tells me we could get some useful work done while we're waiting for this page to be transferred from disk to main memory. And in fact, that'll happen. So what will happen is we're going to just say, hey, this process that generated the address, we are going to go ahead and put it to sleep. And we're going to run another process instead. And that other process, or many other processes in fact, can go ahead and take advantage of these 10 million instructions and get useful work done. Maybe some of them also are going to go through the same process and require waiting on disk. But the nice thing is we have lots of processes that need to run doing their things. And so many of them likely can get useful work done with these many, many, many instructions that we're waiting on. So just keep in mind that fact that sort of between here and here where we're activating the I/O hardware and updating the page table, that we are actually not waiting. We are going ahead and running other processes and waiting, putting this particular process in a state that says, hey, it's waiting for some I/O. Once its I/O is completed, then it'll be eligible to run again. Meanwhile, there are plenty of other processes that can run. All right, we missed one part of this, and that is, let's say there is no free page frame. So we get in here, we try to do a read-write. The page is not in main memory. We want to load it in main memory, but there's no free page. So first, we've got to free up a page. Okay, so the first thing we're going to do is go check and see, is the frame dirty? Is there a free page frame? And the answer is no. And then we look through the frames and say, well, we pick a particular frame that we say we want to get rid of. Right? Remember, we used that LRU, look at the least recently used, or at least not very recently used. So we have a candidate page we want to get rid of. And then the question is that one dirty or not? That is, has it been written since it was last brought into memory? If it isn't dirty, then we can just go ahead and kick it out. Okay? Update the page table to show that it's free, and then go back in, and the CPU can go ahead and read that page from disk. Why can we kick it out? Well, think of this. That frame was loaded into memory from somewhere, right? That frame that is not dirty was loaded into memory, either from an ELF file or from this paging file that the VM system is using to keep track of old pages, or it was loaded from just deciding that it was zeros, and so just doing that from the CPU. But in any case, we can recreate it. We have enough information to recreate it. So therefore, we can just kick it out of memory. If, on the other hand, it's dirty, well, that means it's been written to since the last time we loaded it. That written to contents is only in memory and nowhere else, so we have to save it. So we'll go ahead and basically tell the CPU we want to write this page to disk. Right? That is going to take some time, right? We'll activate some I/O hardware. It's going to transfer it from main memory to the disk. We will then at that point update the page table and then go in and then again go to disk and read the page we're trying to load into memory. So now all of a sudden we have not 10 million instructions, but like 20 million instructions, because we've got to wait here and then we've got another wait here. So again, during this time as well, we are going to be letting other processes run. This process is going to be sleeping, waiting for its I/O to complete. So that is virtual memory. This ability to use a limited amount of physical memory and support processes whose address space may be larger than physical memory, and actually multiple processes, taking advantage of the fact that each process at any given time has kind of a working set of pages that it is using. And as long as that working set is in memory, it can be getting useful things done. The operating system goes ahead and provides this illusion that the entire address space is there and present. It's an illusion that is maintained by the fact that when a process actually goes to read or write any address in its address space, it'll succeed. It just may take longer than it realized because it may actually require I/O of either writing an old page to disk and then reading its page back in, but the instruction that reads or writes to any address space will succeed.